Hello, geometry students. I appreciate you finding time to get your notes taken care of. Today we're going to be looking at some more advanced angles that show up inside of circles. So please copy down your title, More Angles Formed in Circles, and also your objective. And our objective for this day is to discover more advanced angles that are formed by lines interacting with circles. Anytime you need more time during the notes, go ahead and press pause and then hit play whenever you're ready to move on. Okay, so let's start off with a very brief review. Okay, the last time we had a lesson, we were discussing what was the relationship between the angles and the arcs that were formed by line segments coming from common endpoints when they interacted with the circles. Now, obviously, when two lines come from common endpoints, there's an angle that's formed between the two lines, and then there are two arcs that are caught between those two lines when those lines intersect the circle. And we saw that all of these lines, all of these situations had the same rule. And the rule was that the measure of the angle would equal half of the difference of the two arcs. So 1/2 times the measure of the larger of the two arcs, which is the one furthest away from the intersection. And then from that we subtracted the smaller of the two arcs, which is the one closer to the intersection. Okay. Now, what we're going to look at, or what we're going to start off with, is there is another very similar situation that actually uses this rule exactly. However, when we plug this situation into the rule, it comes out looking a little bit different. Okay, and the situation we're going to look at is if a tangent and a chord share a common endpoint. Now, when a tangent and a chord share a common endpoint, the appearance of the situation is different, particularly because the intersection is not outside of the circle like we saw last time. Since a chord does not leave the circle, then the only way a tangent and a chord can intersect would be at the point of tangency. In this case, that would be point B. Okay, so this intersection actually occurs on the circle. However, it uses the same rule. Now, the rule looks condensed here, okay, but let me explain to you what you're actually looking at. The rule says, in this case, the measure of angle ABC, which is at the point of tangency, is going to equal 1/2 of the measure of arc AB. Now, I said that this was the same rule, but as you can clearly see, there is no subtraction in between any two arcs on this one. Okay. Now, the reason for that is this. Okay, looking at the picture, how many arcs are actually caught in between this tangent BC and chord AB? Well, there's only one arc actually in there. Okay, so if you were to try to plug this into the other formula, you would have a large arc, which would be AB, and then your small arc doesn't actually exist, or technically that would make it 0. So you have your large arc minus nothing. So basically you just have the large arc. So it's the same formula, however the small arc does not appear in the formula because there is only one arc to consider. Okay, so if you really get to thinking about it, what this really translates into is kind of a hybrid in between the rule that we saw last time with the difference of the two arcs and the rule that we saw a few lessons ago on inscribed angles, okay, where the angle would actually be half as big as the intercepted arc. So a lot of people actually choose to think of this situation as a different kind of inscribed angle, because after all, it is an angle that has its vertex on the perimeter or the circumference of the circle. Okay, its endpoints are just a little bit different. An inscribed angle has both of its endpoints on the circle. Tangent obviously cannot do that. It is proceeding along the outside of the circle. So either way you want to think about it is fine with me, as long as you get it learned. Now, a completely different situation would deal with this. Okay, we've seen intersections that are outside the circle. We have seen intersections that are on the circle. But what happens if you have an intersection inside the circle? So in this case, let's say that you have two chords that are intersecting. Obviously, when two chords intersect, they're going to intersect inside a circle. Now, when this happens, the angles that are vertical with each other at that intersection have a relationship with their arcs. Okay. And the relationship basically goes like this. Okay, here's a diagram of what we've got going on. Now I've got some color coding happening inside of my diagrams, and I will do that a lot, especially as our diagrams get more and more complicated. So you might want to consider color coding your notes as well. In this situation, we have two arcs, or I'm sorry, two chords, chord AC and chord BD, and they are intersecting at point E. Now at the intersection, point E, obviously there are two different sets of vertical angles that are formed. One of those sets is marked with the little red arcs inside of there, and then there are also arcs that are highlighted in the picture, arc AD and arc BC, that are caught between those two chords the same way that the little red congruency marks are caught in between those two chords. Okay, and those four locations are related like this. Now obviously angle AED and angle BEC at the intersection of the chords, they are congruent because they are vertical angles. We learned that a long time ago. Okay, but the relationship between those vertical angles and their arcs is that the measure of the angle will equal half of the sum of the arcs that are caught between those chords. Okay, now please notice that the formula in this case is not a subtraction problem. It is an addition problem. That is a difference or a change you're just going to have to get memorized. If two lines intersect outside of the circle, then we would be subtracting the two arcs. But if they intersect inside of the circle, we are adding the two arcs. Okay, now this is obviously not the only way that this rule could apply to this picture. We could also look at it from the perspective of the other two angles that are vertical with each other at point E. Okay, and I have them highlighted the same way that I did from above. It's the same circle. It's just going the opposite direction with those vertical angles, which of course changes the arcs. Okay, but those vertical angles caught between the two chords and the arcs that are caught between the two chords, well, they have the same relationship as above. But in this case, angle AEB and angle DEC, they are congruent, of course, because they are vertical angles, and the relationship is that that angle will equal half of the sum of the two arcs caught between those two chords. Okay, now as before, I'm not going to introduce you to a whole bunch of new information today. Okay, so we've got just a couple of new formulas, and let's take a look at how those might apply to some diagrams. Okay, so let's take a peek here. Here we have an example. In our example, obviously we have a circle, we have a tangent, and we have a chord. We are given one of the arc measurements. Arc AB is marked as 126 degrees, and we're told to find the measure of angle CBA. Okay. Now, as always, okay, as you get more and more rules and stuff like that, it's going to get more and more confusing. Okay, and the problems are not going to come out and tell you, oh, on this particular problem, you want to use this formula. It'll be up to you to make the decision what formula should be used based upon the information that you are seeing. So what we need to recognize is that right here we have a tangent and a chord that are intersecting at a common endpoint, point B. Okay, and the connection that you need to be able to make in your mind is that there is a relationship, okay, that the measure of the angle between the chord and the secant, angle ABC, okay, is going to equal half of the measure of the arc, which would be arc AB. Oops. My program messed up on me a little bit right there. Okay, so all we have to do is plug in the information that we need. Well, angle CBA, that's what we're hunting for. Okay, and it should equal half of the arc caught between the secant and the chord, which is the 126 degrees. Half of 126 degrees is 63 degrees. There you go. It's really that simple. Very simple rule. It's just a matter of identifying it when you see it in the problem. Okay, I'm going to give you this example. I'm going to ask you to copy it down and work it out in your notes. Do not turn off the video or tune the audio out just yet. We're not finished yet. Okay, but I want you to copy this example, work it out in your notes, bring it with you completed to class the next time we meet. Press pause if you need more time to copy the diagram. I'm about to turn the page and move on to the next example. Okay, let's look at this one together. Clearly, we have a circle. In our circle, we have two chords that are intersecting. We have various information scattered around the diagram. A couple of arcs that are marked, and an angle measurement at the intersection between the two arcs. That is the goal of the problem. We are trying to solve for x. Okay. Now again, the problems aren't going to come out and tell you what to think or which rule to use. It'll be up to you to identify what's in the picture and then decide the proper rule for yourself. Okay, so clearly we have two chords that are intersecting, we have arcs that are caught between those chords, and we have an angle that is also caught between those chords. Okay, that's an important thing to recognize. Okay, that the arcs that we know, there and there, we have those measurements. Okay, and it is the angle that is in between those chords in the same positioning, okay, is that angle that we're actually searching for. So the rule says the measure of the angle should be 1/2 of the sum of the two arcs. Okay, so let's plug in what we know from the picture. The measure of the angle is x degrees. We do not know what that angle is yet. 1/2 is built into the formula, and then here come the two arcs. Now, it does not matter which one is the large arc or which one is the small arc like it did last time, because we're not subtracting this time. We're not concerned about the angle measurements trying to become negative. They're just going to add up. So all we have to do is simplify the problem. 106 plus 174 is 280, and x is half of 280, which is 140. And there you go, you're done. Again, the math is not difficult. The formula is not all that difficult. It's just a matter of you pulling the correct formula out of your brain in order to get the problem done. The last thing I have for you is this example. Again, I want you to copy this one down. I want you to figure it out and come to class with an answer for this question. Okay, so the audio is going to stop here in a moment. I will leave the video running for a few more seconds so that you'll have time to copy down the diagram. I appreciate you finding time to get the notes taken care of. I will see you in class, and this is the end of the audio.